22.1 Kepler's laws. Johannes Kepler was a German astronomer in the late 1500s. He studied the motion of planets and moons, and he created 3 laws to predict the motion of any satellite. A satellite is an object that is in orbit around another. Generally, satellite motion is a combination of circular motion and gravitational force. Kepler's first law describes the shape of a satellite's orbit. It says that satellites orbit in elliptical paths. So the shape of a satellite's orbit will always be an ellipse, which is a kind of oval, with the sun at one focus. If you're not familiar with ellipses, I've got a quick video to show you how an ellipse would be drawn. The 2 pins in the center of the page represent the 2 foci of the ellipse. You can see the string attached around the 2 foci is stretched, so the pen creates an oval shape. An ellipse is always an oval, where the line from one focus to a point on the ellipse to the other focus will always equal the same amount. So A plus B will always be the same number for any point along the ellipse. This is true for a satellite's orbit as well. The shape of a satellite's orbit is always an ellipse. However, the only difference is the sun is at one focus of the ellipse. So if we draw a line from the planet to the sun and the planet to the other focus, A plus B, those 2 lines will always equal the same number at any point around the orbit. Kepler's second law says that satellites sweep out the same area in the same amount of time. This means if the satellite in its orbit was to create an area over a certain amount of time, no matter where you were in the orbit, during that time period, the same area would be swept out. This is best understood through a picture. So in this picture, we have 3 areas, area A, B, and C. The time to sweep out area A would be equal to the time to sweep out area B and the time to sweep out area C. And these 3 areas are the same area, just different shaped. Kepler's third law is more mathematical. It's a formula. It's t squared over r cubed equals k, where t is the orbital period, how long the planet or moon takes to orbit around the object. R is the average radius of the orbit. And k could be any number depending on the object that's being orbited around, but it will be the same number for that object. This is what we call Kepler's constant. Kepler's constant will be the same for any planet or sun that is being orbited around. Here's an example. Example 1. The average Earth to Sun distance is 1.5 times 10 to the 11 meters. What is k for the Sun? Well, the orbital period for the Earth is 365 days. To get this in seconds, we multiply 365 by 24 hours in a day and 3,600 seconds in an hour. This gives us an orbital period of 315,360,000 seconds. The orbital radius, 1.5 times 10 to the 11 meters, means that t squared over r to the 3 equals 315,360,000 squared divided by 1.5 times 10 to the 11 cubed, which gives us a k for the Sun equal to 3.0 times 10 to the negative 19 seconds squared per meters cubed. This value will be the same for the Sun no matter what object we look at in orbit around it. This is k for the Sun. We can use this value because it will work for any planet or moon orbiting the Sun. We'll use this in a second example. The average orbital distance for Mars around the Sun is 2.279 times 10 to the 11 meters. How long does it take Mars to orbit the Sun? Again, t squared over r3 equals k, but the k value, because it's still orbiting the Sun, is the value we found in the previous example, 3.0 times 10 to the negative 19 seconds squared per meters cubed. We can rearrange this to be t squared equals k r cubed. So t equals the square root of k r cubed. So t equals the root of 3.0 times 10 to the minus 19 times 2.279 times 10 to the 11 cubed. So t for Mars equals 5.965 times 10 to the 7 seconds, which is equivalent to 690 days. It's often useful to define a different unit for space, because space is so large. So astronomers have created a unit that they call the astronomical unit. This unit is a much larger measure of distance. The astronomical unit is equal to the average Earth to Sun distance. And we can use this astronomical unit as a distance unit instead of meters or kilometers. It's just a different way of measuring distance. So the astronomical unit is the average Earth to Sun distance. 1 AU is 1.49 times 10 to the 11 meters. It's very useful for Kepler's law. If we use astronomical units and years in Kepler's law formula to find Kepler's constant, things get a lot simpler. It allows us to get a Kepler's constant for the Sun equal to just 1. I'll show you. Kepler's constant equals t squared over r cubed. Since the time is 1 year, and we're looking at 1 astronomical unit, 1 year over 1 astronomical unit cubed is 1 year squared per astronomical units cubed. It's just 1. It allows us to do calculations much more simply. I'll show you. Example 3. The average Sun-Jupiter orbital radius is 5.2 astronomical units. How long does it take Jupiter to orbit? So t squared over r cubed for the Sun equals 1 year squared per astronomical unit cubed. This rearranges to t squared equals r cubed. Much easier looking. T equals root r cubed. So t equals the square root of 5.2 astronomical units cubed, which gives us time in years 11.8 years to orbit the Sun. Example 4. Pluto takes 248 years to orbit the Sun. Again, as long as we use years in astronomical units, we can use a Kepler's constant value of 1. Again, we can rearrange. In this case, we get r equals cube root t squared. An easier way to write this and put this in a calculator is t to the power of 2/3. R equals 248 to the power of 2 over 3, which gives us 39.5 astronomical units, or 39.5 times the distance from the Earth to the Sun.